the result of a part of the result of this topic, structural response of Kebe State Bridge subjected to blast load. In the structural design, a structure is safe when the actions are lower than the resistance. This is easy to be checked, especially for conventional load. But there are other kinds of load that are not easy to be predicted. So this increases the complexity to check the safety. This kind of load is accidental load. Designed for accidental situations is in particular implemented to avoid structural collapse. The Error Code 1, Part 1.7, is a part of Error Code dealing with the accidental loads and explosions. It is mainly focused on impact actions such as collision between trucks and other types of vehicles. Another impact action that may catch the attention, especially for widely used structure, is blast loading. In this case, the reliability assessment of the structure is more applicable. So the main aim of our project, our work, is to derive the fragility curve of a Kebe State Bridge under blast loading. To do that, we will follow this flow chart. But today we present only the first part of the work, starting by the definition of the material and geometrical parameters, and ending with the definition of the limit state of the bridge through a pushover analysis and the definition of the estimation of the structural demand. So what is a blast load? For the blast happening in a free air zone, it can be modeled as the pressure varying with the time, which reach a point at a certain distance from the detonation. It is characterized by the mass of equivalent TNT, by the standoff distance, which is the distance between the point of detonation and the impact point of the structure, the arrival time, which is the distance, the time between the time of detonation and the time where the pressure becomes higher, and the positive and negative duration, this is the positive duration and this is the negative duration. So the bridge is, in our study, is defined by two lateral span of 100 meters and one central span of 200 meters. The 3D frame of the bridge is presented in this image. So we have defined a closed box section for a pylon, for transverse, and for the deck. For the cable, we use a circular section. We consider also a perfect elastoplastic strain diagram for the structural element. While for the cable, we consider only an elastic part of the structural element of the cable. This is the geometrical characteristic. This table presents the geometrical characteristic of the structural element used. Then, for this pushover analysis, we observe different situations. In fact, we observe that for the result in terms of shear and in terms of bending, we have that the ductility of the structure depends on the situation where the load is located. So, when the load is located close to the abutment, we have a different ductility when the load is located to the midspan. We also observe that for the case of when we are studying the shear to the structure, a small displacement will lead to the structure, to the failure of the structure, while when the load is applied at the midspan, a large displacement will lead to the failure of the structure of the bridge. The observation is different for what regards the bending, because we observe that at the close of the abutment, a large rotation will lead to the failure of the bridge because the abutment was defined as a simple support. So it was released the rotation about the transverse direction. Then we collect the displacement after the nonlinear dynamic analysis. We observe that for the detonation happening close to the deck, we have a large displacement. Than for this is when the standoff is small, it means that the detonation happens close to the deck. When standoff is large, the detonation happens far to the deck. So the detonation happens at 1 meter to the deck, and the detonation happens at 2 meters to the deck. So we observe that impact close to the deck produce more effect in terms of vertical displacement of the deck at the local region. Considering the result from the pushover analysis, it is possible to predict which action will produce the failure of the deck. So after we define the limit state for load acting at the abutment and the limit state for load acting at the midplane, we define 3 different types of damage, from moderate to collapse. And we consider only the rotation as a condition of damage. So for the rotation being between 2.9 and 5.6, we have a moderate damage. From the rotation being larger than 9, we have a collapse. When the load is applied at the abutment. Then after doing the nonlinear dynamic analysis, it was possible to collect the different value of rotation and to determine the frequency of the collapse or the frequency of each damage state. So we observe that when the load is applied close to the deck, we have more frequency to have the deck to collapse. When the load is applied far to the deck, we have a large frequency to have a moderate damage. And for what requires the stress, it is obvious that due to the dynamic rate of the load, we expect the structural component goes to the plastic yielding. But to know the probability to have fully yielding section, we then perform the analysis and then collect in terms of the mass of the action and in terms of the standoff distance. We observe that when the action is happening at the midspan, the section goes in fully plasticization fastly than when the action is happening close to the abutment. But it's also important when investigating the effect due to blast loading to consider also the strain reserve of the structural element. Then we also collect the strength of the structural element, and we observe is total breakage of the deck for some situation. For the case where the mass is 1,000 kilograms and where the mass is 1,500 kilograms. This is when the action is happening close to the abutment. When the action takes place at the midspan, you observe a more severe situation. So for the action taking place at the midspan, you observe the mass from 500 to 1,500 will lead to a total breakage of the deck. So at the end, we conclude that the impact loading involved in a blast loading can be dramatic for even those structures like Keble Stay Bridge. The damage observed in the local region of the deck is more severe when the action is targeted close to the deck. It is also important to evaluate also the strength state of the structural component when assessing the performance of the bridge on the blast loading. As future works, we will integrate the uncertainty in terms of material and geometrical characteristics, perform the Monte Carlo simulation, and derive the blast fragility curve for Keble Stay Bridge. Thank you for your kind attention.
Thank you. there any questions?